All right, this one may be a little bit of a short one, but we also need to talk about the energy that's stored in an inductor by the current that's flowing through it. And remember that the power that's delivered to an object is minus the current times the potential difference. Because current times potential difference, remember for a resistor, that's the power that leaves the system, right? That's the heat that's produced that comes out. So the minus sign describes how much energy gets put into it. Um, so then to end up finding your work, then you take the integral of what you get from when you had something turned off going that would go through the inductor to when you turn it on. So an example would have been that charging RL circuit, but any situation where you start with no current and then you end up with some current that's not, the same formula will still work. So it's a general equation. So we end up taking the integral from whenever it's completely off to whenever it's fully on and nothing is changing anymore. So we take the integral then from time equals 0 when you close a switch to time equals infinity because you leave it going forever. Then that will be the integral of your I delta V dt because, of course, the integral of power is work. Your delta V, we already had that formula we already came up with, was minus L di dt. So we multiply those things together and we get Li di dt times dt. And that one is one of them. Again, we've seen this a lot of times before. It will be convenient to end up doing a use substitution that you all like to do from calculus. It's just change of integration variables. Di dt times dt, we end up turning it to di, but then we have to end up carefully keeping track of what my current then at t equals 0, which is the lower limit, and at t equals infinity at the top limit. So in that situation, you start it from no current, and we end it with my maximum current, which is often we'll drop the max. It's just this was the process of getting there, and so when we're looking for how much energy is in it, the current's already going, so it's whatever the max is. It's whatever the current is actually going through it. So then the integral becomes really easy, and you end up getting 1/2 L times I squared. So that ends up being the total amount of energy stored in an inductor. That's since this one was really short, I'd mentioned something that was interesting that could happen with mutual inductance. It's not really in this category, but like I said, mutual inductance is not going to be something on your exam. One sort of interesting thing that can happen, if you've heard of what's called evolutionary computing, this is where you end up starting basically software from basically blank code. You end up putting in random bits into it, then try to execute the code. And that a lot of times nothing will happen, which is fine. And what you end up doing then, it's a survival of the fittest. You end up, if you get something that does some effect versus none, then you'll end up keeping something that does something, and then you end up having that end up sharing code, meshing it together with another one that works, and then you end up seeing among the daughters, which thing may end up doing better. You add some more randomness to it, and eventually you end up coming with something that maybe will sometimes work. And what was going on here was somebody decided to try to end up doing this where they were going to end up having to detect sound. And of course, if you've got a microphone, there's nothing terribly exciting about being able to collect information that way. But here they ended up hooking up a computer and they picked a particular frequency. They ended up plugging in the computer and did not plug in a microphone. And so they were wanting to end up saying, okay, can we end up making this with evolutionary methods? Can we end up making it end up being able to hear a microphone? We turn on to this frequency even though there is no microphone coming in. And sure enough, after enough cycles, they were able to actually get something on that computer that ended up doing it at this particular frequency. And it was, which is a very, very strange thing. And when they were taking apart the code in terms of understanding it, because again, remember, you're not coding it there. You're allowing it to be totally random, so you're not following what happens. You might look at it at the end, but you do nothing in between. When they looked at it in the middle, there was something really, really odd that was happening. That you ended up having instructions basically over in this one region, and you had a bunch of instructions somewhere else that had no connection at all. There was no input, no output from this other thing over here to the side. And so they said, well, sometimes you get just random junk that will pop in, like junk DNA or something. So they try to extract it, and you extract it, it does not work at all. Nothing happens. And they rack their brains, what the heck is going on? What turns out, you ended up having this little piece of program over here, the main one, and you had this other weird piece over here that seemed not to be able to do much, but somehow was critical to the process. So what happens is you end up getting execution through this code and just whatever stuff, and that in this situation you had current that was flowing through this, so you end up getting magnetic. You get the mutual inductance with this other code over here, which would then execute something, and then its current would send information back over here. And the reason why this would work is that whenever you have sound in traveling through a piece of solid changes the distance. It ends up wobbling it. So by doing this, you'd end up changing the amount of current from one part to the other. So over the time period of an oscillation of this, you have quite a bit of time, because computers were fast, have quite a bit of things that you'd be able to detect between whenever it would bounce one side versus the other. And then it could end up hearing the difference in that mutual induction that you ended up getting. So, like I said, normally mutual induction is something that you don't want, but that's kind of a cute little way that that ended up coming up, that where mutual induction, it's not terribly useful, but it shows you something where in mutual induction sometimes does things that are really strange, which is not always good, but that's what it is. All right. Next time we're going to look at when we mix an inductor and a capacitor together. We get something that's a lot different from what we've seen before, in one sense.